Black holes, from scientists to nerds, we all love them. It is an extreme object, it has enough gravitational pull to prevent light from escaping, which is the fastest object in the universe and thus breaks several laws of physics. But do you know exactly how many zeros it has in its mass? To be more specific, I mean how enormously heavy they are. A black hole is formed due to the existence of gravity. A star is a large mass of hydrogen gas pulled together with gravity. Normally this would directly result in black holes, but due to intense temperatures they obliterate and form helium instead, releasing enough energy to counteract gravity, but sadly all hydrogen runs out and it collapses, but it doesn't always turn into a black hole. Why? Well, to not bore you with math, you need to be fat enough and the sun isn't. Okay, now that we've successfully increased the length of this video, we now know what a black hole is. So, because your mass doesn't matter when you're being pulled due to gravity, you need to acquire a certain speed to escape the gravitational force. This is calculated by this formula. This speed is called escape velocity. Let's assume our radius as r and make a black hole with the Statue of Liberty. So, its mass is 225 tons or 225,000 for our formula and make the escape velocity to be light speed. So what do we get? Well, the g is known as the gravitational constant and it's approximately 6.67428 into 10 to the power of minus 11. Doing the math, we get a bit smaller than 600 yoctometers, which is about 420,000 times smaller than an electron. Well, that was just a foreshadowing to the enormous mass of black holes. Now let's assume mass to be x and make a black hole of radius 1 meter. Doing the math, we get a bit more than 674 septillion 228 sextillion 9 quintillion kilograms, which is 112 times heavier than Earth. Sadly, the Sun is 3,000 something times heavier. Remember how I said escape velocity to light speed? That just means light can escape, but I added a bit more, so it's correct. Now let's calculate density. So we get 4.188 cubic meters, so the density would be something like 160 quintillion 960 quadrillion 81 trillion kilograms per cubic centimeters, but that's just the density of a unit radius black hole. Let's find that of a 2-meter radius black hole and we get 40 quintillion 240 quadrillion 20 trillion 300 billion kilograms per cubic centimeters, which is less than the previous, but that's just because the mass increases in a linear manner but volume increases in an exponential manner, so the ratio between radius and density is approximately 160 quintillion 960 quadrillion 81 trillion divided by radius squared, in meters, squared is to radius, in meters. If you want the ratio to nearest units and not trillions, try to use a non-rounding calculator or do it yourself. So that was pretty heavy, huh? Well, that's just about it. Oh yes, trivia, because of this silly ratio, the heaviest black hole Phoenix A has a density of just 30.9 grams per cubic meter, which is a significant downgrade. But as it turns out, to compress something to such small size, you need force and most preferably gravitational force, which is how they form, and gravity does not care that it has enough gravity to stop light and compresses it according to its mass. So what we found here is the maximum size we need to compress an object to get a black hole, and the lightest a black hole of a certain size can be. And I disagree with those scientists who use the same formula as I did, who say that this is definitely the mass of any black hole. So let's do something. Let's find the black hole of a star with mass x and this radius r and find out the ratio. Now here's the formula to find the change in volume. The pressure is force by cross-sectional area, and so the formula becomes this. How to find the force? Well, I was thinking for 2 hours before coming to the conclusion to use acceleration into mass, so we use this formula to find the acceleration, which is this, and this is the pressure. And the original volume is this. Bulk radius is the ratio between force and change in volume of a specific material. Since stars in their deathbed are composed of helium, we'll use bulk radius of helium over here, and now the formula is this. And now let's simplify. Multiply the denominator, multiply the fraction, and multiply the denominator. So, this is the change in volume and this is the volume of the black hole, and now the density is this, and let's find the radius of the black hole. Let's set radius to a, and here's the formula for volume. So solve for a, multiply this, multiply by 3, divide by 4 pi, and now we have the ratio as this. Simplify further if you want. You may argue that we see because of light and a little distance away from the black hole the gravity decreases enough for light to escape and reach our eyes, but the actual radius of the black hole is smaller than what we see because in the area between what we see and the actual black hole is where the escape velocity is more than light speed but less than the maximum escape velocity created by its velocity. But do feel free to correct me if you want. But anyway, I should probably stop this video. Hope you learned something.
But a black hole is defined as a region in spacetime from which no light can escape, so we only count what we see.
You are correct. In that case, use the formula I derived earlier. But the thing is that I do not believe in singularity because the size of a black hole increases with consumption of matter. Due to gravity, the object flattens and just falls on the black hole's surface. I believe when a star dies it remains helium and just gets compressed to a smaller ball, and even a considerable distance away from it light is unable to escape, that is, we cannot see the inner ball or the physical black hole surface. Let's call this the star's dead body for now. So you see, in my ratio for the star's dead body I did not realize that the pressure changes because when the black hole gets compressed, its radius decreases and therefore both the force and cross-sectional area decrease and thus decrease change in volume. So I will find the real radius density ratio in another video. As you can see, this video is getting longer, so I will stop it here.